Hello, this is lecture 7.3 of the GPU teaching kit. We'll be presenting atomic operations in CUDA. The objective of this lecture is to learn to use atomic operations in parallel programming. We're going to start with the key concepts of atomic operations, and we will show the different types of atomic operations in CUDA. We show how a CUDA programmer can use intrinsic functions to perform atomic operations in kernels, and we show a basic histogram kernel that uses atomic operations to ensure good outcome. This slide reviews the concept of data race. We see that one of the threads starts its read, modify, write sequence, and another thread starts its read modify sequence before the first thread has the chance to complete its sequence. As a result, both threads receive 0 value in their old variables, and the value of memory location X becomes 1 after the whole entire sequence. And this is a bad outcome. Atomic operations are designed to ensure good outcome of read, modify, write operations. An atomic operation is a read, modify, write operation performed by a single hardware instruction on a memory location address. The instruction will read the old value, calculates a new value, and writes the new value to the location. The hardware will ensure that no other threads can perform another atomic operation on the same location until the current atomic operation is complete. Any other threads that attempts to perform an atomic operation on the same location will typically be held in a queue. As a result, all the threads will perform their atomic operations serially on the same location. One atomic operation will finish before the next one can begin. Now that we understand that an atomic operation is a hardware instruction that performs a read, modify, write sequence on a memory location, the question is, how can we perform such an atomic operation in a high-level language like CUDA? The answer is actually quite simple. We can perform an atomic operation in a CUDA kernel by calling functions that are translated into single instructions. And these instructions are called intrinsic functions or intrinsics in literature. In CUDA, there are atomic add, subtract, increment, decrement, minimal, maximal, exchange, and compare and swap atomic operations. And all these atomic operations can be performed by calling their respective intrinsic functions. And you're encouraged to read CUDA C Programming Guide 4.0 or later for details. In this lecture, we're going to be focusing on atomic add operation. And the atomic add operation in CUDA can be performed on an integer variable in the global memory or shared memory by calling atomic add intrinsic function with two arguments. One is an integer pointer to a variable in the global memory or shared memory, and the second argument is the integer value, which will need to be added into the memory location. So the semantic of the function is that it will read a 32-bit word old from the location pointed to by address in the global or shared memory. The function will compute old plus value and stores the result back into the memory location. And then the function will return the old value. All this is actually going to be translated into an atomic add integer instruction in the hardware. The atomic add operation in the previous slide operates on a signed 32-bit integer variable in either global memory or shared memory. We can also perform atomic add operation on other data types in global memory or shared memory. We can have unsigned 32-bit integer atomic add, unsigned 64-bit integer atomic add, and on some of the more recent CUDA devices, we can perform single precision floating point atomic add. So all these atomic adds can be performed on the particular kind of data type that we need to perform read, modify, write sequence on. Understand how to use atomic operations in a CUDA kernel, we're ready to complete a basic text histogram kernel. At the beginning of the kernel, every thread will calculate a unique linearized index I. And it will also calculate a common stride, which is the total number of threads in the grid. The loop in the kernel implements the iterations for processing the input string that we covered in one of the previous lectures. During the first iteration, all the threads will use their unique I value to fetch an input character from the first section of the input buffer. And we assume that the characters are in the ASCII code format. In ASCII code representation, the alphabet letters are encoded in 26 consecutive code values. So even though we don't know exactly what these code values are, if we take the character value and subtract it by the ASCII code value for letter A, the difference should range from 0 to 25 if the input character is indeed an alphabet letter. So that's why the next if construct tests for the condition of the alphabet position is greater than or equal to 0 and the alphabet position has to be less than 26. If the condition is met, then the thread will increment the appropriate bin counter value by 1. And the bin index is calculated by dividing the alphabet position by 4. This is because we define the bin as 4 consecutive alphabet letters. So A, B, C, D should all belong in bin 0, and E, F, G, H should all belong in bin 1. By dividing the alphabet position by 4, we will lump all the every 4 letters into a bin, and that's how we calculate the appropriate index for the bin counter. After the first iteration, all the threads will move on to the next section by adding stride to their unique index. Remember that the stride is the total number of threads in the grid. This process will repeat for every thread until each thread's unique index is greater than size. That's when the thread will complete execution. When all the threads' unique indices are greater than or equal to the size, then the kernel will terminate execution. So this gives us a basic histogram kernel. Lecture 7.3. Thank you.